So here's something worth thinking about as you settle in tonight. Right now, at this very moment, there are systems all around you that are quietly watching, listening, and learning. Not in any sinister way, nothing dramatic. But your email app spent today sorting through the messages that came in, deciding which ones were important and which ones were spam. And the thing is, it's getting better at that every single day. Nobody sits at a desk somewhere writing new rules for it. It just learns. The map on your phone is predicting how long your commute will take tomorrow morning based on years and years of traffic patterns it has absorbed. Millions of trips taken by millions of people, all distilled into a single estimate that shows up on your screen before you even ask for it. Somewhere right now, in a hospital you'll probably never visit, a program is looking at a chest X-ray and noticing a faint shadow that a tired radiologist, at the end of a 12-hour shift, might have missed. And in a server farm humming away in the middle of Oregon or Iowa or somewhere in Finland, a program is reading millions of sentences in dozens of languages, slowly building something that looks an awful lot like an understanding of how human language works. All of these things are happening because of a single, deceptively simple idea. The idea that you can build a machine that gets better at something not by being told the rules, not by having a programmer carefully write out every possible scenario, but by showing it thousands or millions or billions of examples and letting it figure out the patterns on its own. That idea is called machine learning, and it is, quietly and without much fanfare until very recently, one of the most transformative ideas that human beings have ever had. And that's what we're going to talk about tonight. The whole thing. How it started, where the ideas came from, who figured them out, what went spectacularly wrong along the way, and how we ended up living in a world where a computer can look at a photograph and tell you what's in it, or listen to your voice and understand what you're saying, or write a paragraph that sounds so much like a person wrote it that you genuinely can't tell the difference. We're going to take it slow. We're going to start at the very beginning, which is actually much further back than most people realize, and we're going to walk through it together, one idea at a time. If you drift off somewhere along the way, that's perfectly fine. That's kind of the point. The ideas will be here whenever you come back to them. And honestly, some of this stuff makes more sense when your mind is loose and relaxed and not trying too hard to force things into neat categories. Let's start with a question that sounds simple, but turns out to be surprisingly deep. What does it actually mean to learn from data? That phrase gets thrown around a lot these days: machine learning, data-driven, learning algorithms. And it sounds straightforward enough. But when you really sit with it, it's a profound idea. And the roots of it go back centuries. Long before anyone had a computer. Long before anyone had even imagined an electronic machine that could calculate anything at all. The roots go back to a very human problem. How do you figure out the truth when you're uncertain? How do you make good predictions when the world is noisy and messy and unpredictable? Imagine you're living in 18th century England. It's the 1740s. There's a Presbyterian minister named Thomas Bayes living in Tunbridge Wells, a quiet spa town southeast of London. He's not famous. He's not at a prestigious university. He doesn't have wealthy patrons or powerful connections. He's just a clergyman with a sharp mind and a deep fascination with the mathematics of chance and uncertainty. And Bayes is thinking about a problem that sounds almost trivially simple, but turns out to have enormous consequences for the entire future of science. If you observe some evidence, some data, how should you rationally update your beliefs about the world? Here's a concrete way to think about it. Say someone hands you a coin and you want to figure out if it's fair. You flip it 10 times. It comes up heads 7 times. Is the coin biased? Well, probably, you'd suspect. 7 out of 10 is a bit suspicious. But you're not certain. A perfectly fair coin could come up heads 7 times out of 10 by sheer luck. It's unlikely, but it's not outlandish. Now imagine you flip it 100 times and get 70 heads. Same ratio, but now you're much more confident something's off. And if you flipped it 1,000 times and got 700 heads, you'd be virtually certain the coin was biased. Your confidence depends on how much evidence you've gathered. More data, more certainty. That's the intuition. And what Bayes did was work out a rigorous mathematical framework for exactly this kind of reasoning. A precise formula that takes your prior belief, your initial guess about how the world works, and then updates it based on new evidence to give you a posterior belief, an improved estimate that properly incorporates what you've just learned. The math is clean, elegant, almost inevitable once you see it, and the idea is so fundamental, so broadly applicable, that it sits at the very heart of modern machine learning 3 centuries later. Every time a spam filter sees a new email and updates its estimate of whether certain word combinations indicate junk mail, it's doing something that traces directly back to Thomas Bayes. Every time a medical diagnostic system adjusts its estimate of whether a patient has a particular disease based on a new test result, it's using Bayesian reasoning. The idea is everywhere. But here's a lovely historical irony. Bayes himself never published this work. He apparently didn't think it was finished. Or maybe he wasn't confident enough in it. Or maybe he was simply a perfectionist who couldn't bring himself to send it out into the world. Nobody knows for certain, because Bayes left very little in the way of personal correspondence or diaries. After he died in 1761, his friend Richard Price, a Welsh philosopher and mathematician in his own right, found the manuscript among Bayes's papers, recognized that it contained something important, polished it up, added his own commentary, and sent it to the Royal Society, where it was read and discussed. And then, remarkably, it was mostly forgotten for decades. The mathematical world wasn't ready for it. There wasn't a practical context in which people needed to systematically update beliefs from data. That would come later. The idea had arrived too early, like a letter delivered to the wrong address, and it sat there patiently, waiting for someone to realize it belonged to them. Now, fast forward about 50 years to the very early 1800s, and a completely different kind of problem is driving a different kind of mathematical breakthrough. Astronomers across Europe are trying to track the orbits of planets, comets, and the newly discovered asteroids, and they have a practical difficulty that is driving them mad. Their measurements are noisy. Every time you point a telescope at a celestial body and try to pin down its exact position, you get a slightly different answer. The atmosphere shimmers and wobbles. Your instruments aren't perfectly calibrated. The clock you're using to time the observation might be off by a fraction of a second. Your eye tires and your hand shakes during a long night of observing. So instead of one clean, definitive measurement, you end up with a scatter of slightly different readings, a cloud of data points, and you need to figure out the best estimate, the most probable true position, from all that messy, contradictory information. And 2 mathematicians, working independently, in different countries, without knowing about each other's work, came up with essentially the same brilliant solution. Carl Friedrich Gauss, in Germany, and Adrien-Marie Legendre, in France, both developed what we now call the method of least squares. And by the way, their priority dispute over who invented it is one of the great arguments in the history of mathematics. Legendre published first, in 1805, in a book about determining the orbits of comets. He described the method clearly and used it effectively. But Gauss claimed in print, a few years later, that he had been using the technique privately since the late 1790s, when he had used it to predict the orbit of the asteroid Ceres, an extraordinary feat that made him famous across Europe. Whether Gauss truly had the method that early is still debated by historians. He was certainly brilliant enough. Gauss was, by any reasonable measure, one of the greatest mathematicians who has ever lived. His contributions span number theory, algebra, statistics, geometry, magnetism, optics, and astronomy. He's sometimes called the Prince of Mathematicians. But he was also notoriously secretive about his methods, fond of publishing beautiful results without showing the messy work behind them. He once compared this to the way an architect demolishes the scaffolding after the building is complete. You see the elegant structure, not the process that created it. Which is poetic, but didn't help his case when Legendre got understandably irritated about the priority claim. Regardless of who came first, the idea itself is beautiful and simple. You want to find the curve, the line, or the parabola, or whatever shape your model predicts, that comes as close as possible to all your data points simultaneously. And, as close as possible, is defined very precisely. You minimize the sum of the squared differences between your predicted values and your actual observations. Each data point has a residual, the gap between what your model says and what you actually measured. You square each residual, which makes positive and negative errors both count as positive, and which penalizes big errors more than small ones. Add them all up, and find the model parameters that make that total as small as possible. You're looking for the best fit, the answer that's least wrong, on average, across all your data. And here's the thing, that procedure, finding the model that best fits the data by adjusting its internal parameters, that is learning. In a very real, very fundamental sense, that is exactly what machine learning does. You have data, you have a model, with knobs you can turn. And you turn the knobs until the model's predictions match the data as closely as possible. Gauss and Legendre were doing machine learning in 1805. They just didn't have machines. The arithmetic was done by hand, painstakingly, by candlelight, with quill pens and ink that probably smudged. And the method of least squares isn't some quaint historical artifact that's been replaced by fancier techniques. It's still used every single day in every field of science, engineering, and data analysis. It's the mathematical backbone of linear regression, which is probably the single most widely used statistical technique in the world. When an economist tells you that GDP grows at a certain rate per year, or a climate scientist reports that global temperatures are rising at a certain fraction of a degree per decade, or your doctor says that a certain blood marker correlates with disease risk, they are very often, whether they think about it or not, using a technique that Gauss and Legendre developed to track comets during the Napoleonic Wars. And then, a few decades later, another piece of the puzzle fell into place. In the 1880s and 1890s, a Victorian polymath named Francis Galton was studying heredity, how traits pass from parents to children. Galton was Charles Darwin's half-cousin, enormously wealthy, endlessly curious, and a compulsive quantifier. He measured everything he could get his instruments on. He once tried to create a statistical beauty map of the British Isles. By secretly rating the attractiveness of women he passed on the street in different cities, which gives you a sense of both his inventiveness and his problematic approach to science. He invented the weather map. He pioneered forensic fingerprinting, and in the 1880s, he was gathering massive amounts of data on the heights of parents and their adult children, trying to understand the mechanics of biological inheritance. And Galton noticed something subtle, but enormously important. Tall fathers tended to have sons who were taller than average, yes, but not quite as tall as their fathers. Short fathers had sons who were shorter than average, but not quite as short. The children's heights consistently drifted, or regressed, toward the overall population average. He called this regression toward the mean, and it turns out to be one of those statistical phenomena that shows up absolutely everywhere once you know to look for it. A baseball player who has an extraordinary season will almost always have a more ordinary follow-up, not because they got worse, but because some of their exceptional performance was luck, and luck doesn't repeat reliably. A stock that vastly outperforms the market one year will tend to be more average the next. The mathematical technique Galton developed to study this phenomenon, to quantify the relationship between one variable and another, between cause and effect, between predictor and outcome, he called regression, and that word stuck. When anyone today talks about running a regression, fitting a regression model, doing regression analysis, they are using a word and a mathematical framework that traces directly back to Francis Galton, measuring people in Victorian England. So by the end of the 19th century, you have these mathematical threads weaving together. Bayesian reasoning, the principled updating of beliefs in light of new evidence. Least squares, finding the model that best fits your data. Regression, quantifying relationships between variables so you can predict one from another. All of them are, at their core, about the same fundamental activity, extracting patterns from noisy data, looking at what has happened and using it to predict what will happen next. But for more than a century, this was the exclusive domain of human beings. Statisticians hunched over desks, doing laborious arithmetic by hand, working through calculations that might take hours or days for datasets of a few dozen points. The methods were powerful in principle, but brutally limited in practice by the sheer tedium of manual computation. What was needed, obviously, was a machine that could do the calculating, something fast, something tireless, something that could handle thousands of numbers without making errors or needing to sleep. And that need brings our story to the 20th century, and to the person who, more than anyone else, saw what was coming. Alan Turing. If you know anything about the history of computing, you know this name. Turing is the founding figure of computer science. In 1936, when he was 23 years old, a graduate student at King's College, Cambridge, he published a paper on mathematical logic that essentially invented the concept of the computer as we know it. The Turing machine, his imaginary device of a read-write head moving along an infinite tape, was a theoretical construct, but it defined computation. It established, with mathematical rigor, what it means for something to be computable, and Turing went on to play a crucial role at Bletchley Park during the Second World War, where he led the effort to break the German Enigma cipher, work that Churchill reportedly said shortened the war by 2 years. After the war, Turing helped design actual electronic computers at the National Physical Laboratory in London, and then at the University of Manchester. But here's what matters most for our story tonight, and what is much less well known. Turing wasn't content with machines that simply followed instructions. From very early on, he was fascinated, almost obsessed, by the question of whether machines could learn. Not just calculate, not just follow a program someone wrote for them, but actually change, adapt, improve, through experience, the way living creatures do. In 1947, in a lecture to the London Mathematical Society, this is just 2 years after the end of the war, at a time when the vast majority of people on Earth had never seen or even heard of a computer, Turing laid out 2 possible approaches to creating intelligent machines. The first was what you might call the top-down approach. Program every possible response into the machine. Write an exhaustive set of rules covering every situation. Turing compared this to giving a child a complete encyclopedia and expecting them to be educated. It's comprehensive, but it misses something essential about how knowledge actually works, how understanding actually develops. The second approach, and this is the one Turing found far more promising, was to build a relatively simple machine and then educate it. Let it interact with its environment. Let it try things and fail. Let it receive feedback, reward for good outcomes, correction for bad ones, and gradually adjust its behavior in response. Let it learn from experience, the way a child learns to walk, or to speak, or to read social cues. Turing even sketched out, in broad terms, what such a process might look like: a system of pleasure and pain signals that would shape the machine's behavior over time. He was describing, in embryonic form, what we would now call reinforcement learning, a technique that, 75 years later, would be used to train systems that can play games at superhuman levels, control robots, manage power grids, and navigate complex environments. Think about how extraordinary that is. In 1947, most people in the world had never seen a computer. The first general-purpose electronic computer, ENIAC, had been built only 2 years earlier. It weighed 30 tons, filled a large room, and used about 18,000 vacuum tubes. And Turing, already, is looking past the question of whether machines can calculate and asking whether they can learn, whether they can be educated, like children, whether experience could be, for a machine, what it is for a living creature, the source of capability, not just data. Turing also, in 1950, published his most famous philosophical paper, Computing Machinery and Intelligence, in which he proposed what we now call the Turing test, the idea that if a machine could converse with a human judge through text, and the judge couldn't reliably tell whether they were talking to a machine or a person, then the machine should be considered intelligent in any meaningful sense. He anticipated nearly every objection people would raise. Machines can't be creative, machines can't feel, machines can't really understand, and offered thoughtful, sometimes playful responses to each. He predicted that by the year 2000, a machine would be able to fool a human judge about 30% of the time in a 5-minute conversation. That prediction turned out to be approximately right, depending on how you set up the test, which is either impressive foresight or a lucky guess, or maybe a bit of both. Turing died in 1954, at the age of 41. He was found dead from cyanide poisoning. 2 years earlier, he had been prosecuted for homosexuality, which was a criminal offense in Britain at the time, barbarically, and was sentenced to chemical castration, forced to take estrogen injections that caused physical changes he found deeply distressing. The official verdict was suicide, though some historians have argued it may have been accidental. Either way, it remains one of the most agonizing losses in the history of science. Turing never got to build the learning machines he had imagined. He never saw any of the things that his ideas would eventually make possible. But the vision was out there. The seed had been planted. And it was picked up, remarkably quickly, by a man named Arthur Samuel. Samuel was an electrical engineer at IBM, a practical, hands-on engineer, not a theoretician. In the early 1950s, he was looking for a way to demonstrate the potential of IBM's computers to a public that was mostly confused and slightly frightened by them. And he decided to build a program that could play checkers. Now, checkers might sound like a modest ambition, but consider the challenge. The brute force approach, examining every possible sequence of moves to find the best one, was completely impossible. There are approximately 500 billion possible positions in checkers. That number, 5 times 10 to the 20th, is so absurdly large that you couldn't search through them all if you used every computer on Earth, from now until the sun burns out. So Samuel did something inspired. He wrote a program that could evaluate board positions, a scoring function that estimated how good or bad a given position was, based on features like the number of pieces each side had, how many kings, how well placed the pieces were. And then he let the program play against itself, game after game after game, thousands of games, and after each game, it would go back and adjust its scoring function. Positions that had appeared during winning games got their scores nudged upward. Positions from losing games got nudged down. The program was learning from experience, not following a fixed set of instructions written by a human, but discovering, through its own practice, which patterns led to victory and which led to defeat. And it worked. It genuinely, demonstrably worked. By 1959, Samuel's checkers program could beat many good amateur players. It appeared on national television, on a CBS program, playing against a human opponent, and the audience was mesmerized. Here was a machine that was getting better at something through practice, not programming. And Samuel, in describing what his creation did, coined a phrase that would become the name of an entire field of study. He defined machine learning as the field that gives computers the ability to learn without being explicitly programmed. That's 1959. And that definition is still essentially the one we use today, 65 years later. The crucial word is without. The machine isn't told the answer. It's shown examples, and it finds the patterns itself. That's the core idea. Everything else is details. Now, right around the same time Samuel was teaching his computer to play checkers, something else was happening that would turn out to be even more consequential, though nobody could have known it at the time. At the Cornell Aeronautical Laboratory in Ithaca, New York, a psychologist named Frank Rosenblatt was building a machine called the Mark I perceptron. And the perceptron is where the story of neural networks begins. The story that leads, through decades of drama and setback and eventual triumph, to the AI systems that are transforming the world right now. So let's slow down and really look at what a perceptron is, because the core idea is genuinely beautiful, and it's important to understand it properly before we watch it get attacked and nearly destroyed, and then, decades later, reborn in a form more powerful than anyone had imagined. Rosenblatt was inspired by neuroscience, specifically by a simplified model of how the brain processes information. In your brain, you have roughly 86 billion neurons, each connected to thousands of others through junctions called synapses. A neuron receives incoming signals from many other neurons. Some of those signals are excitatory. They encourage the neuron to fire, to become active. Others are inhibitory. They discourage it. The neuron effectively performs a kind of vote count. It adds up all the incoming signals, weighting each one by the strength of its synapse, and if the weighted total exceeds a certain threshold, the neuron fires, sending its own signal onward to the next layer of neurons. This is a hugely simplified picture of what actually happens in the incredibly complex electrochemical machinery of the brain, but it captures something essential, the idea of weighted inputs being summed and compared against a threshold to produce a decision. Rosenblatt took this biological inspiration and turned it into a mathematical model. His perceptron receives several numerical inputs, each one multiplied by a weight, a number that represents the importance of that particular input. It adds up all the weighted inputs, and then it makes a simple binary decision. If the total exceeds a threshold, output a 1. If it doesn't, output a 0. Yes or no. Fire or don't fire. Cat or not cat. Spam or not spam. And here's the key part, the part that makes it a learning machine rather than a fixed calculator. You show the perceptron an example, and check whether it got the right answer. If it did, you do nothing. The weights are working. If it got the wrong answer, you adjust the weights. You nudge them, by a small amount, in the direction that would have given the correct answer. Then you show it another example. Adjust if needed. Another example. Adjust. You repeat this hundreds or thousands of times, and gradually, through this patient process of repeated small corrections, the weights converge on values that allow the perceptron to classify things correctly. It learns. Rosenblatt built a physical machine to demonstrate this. The Mark I perceptron was a 5-ton device with a 20 by 20 grid of 400 photocells, essentially a very crude digital camera, connected to a network of artificial neurons implemented in analog hardware, with motorized potentiometers that physically rotated to adjust the connection weights. He showed that this machine could learn to distinguish simple visual patterns, like identifying whether a shape appeared on the left or right side of the input grid, and the press coverage was explosive. The New York Times ran a story announcing that the Navy, which was funding Rosenblatt's work, had revealed a machine that could learn by doing. The article breathlessly implied that this was the dawn of machines that could walk, talk, think, see, and even reproduce themselves. Rosenblatt himself, who was charismatic, enthusiastic, and quotable, made sweeping predictions about what perceptrons would eventually achieve. For a brief, heady period in the early 1960s, neural networks were the most exciting thing in computing. And then the whole thing fell apart. It happened because of a book published in 1969 by two of the most formidable intellects in the history of artificial intelligence, Marvin Minsky and Seymour Papert, both at MIT. The book was called Perceptrons, and it was a masterpiece of mathematical analysis, rigorous, elegant, and utterly devastating. Minsky and Papert proved, with ironclad mathematical proofs, exactly what a single-layer perceptron could and could not do. And the limitations were severe. A single perceptron can only classify data that is linearly separable, meaning you can draw a straight line, or, in higher dimensions, a flat plane, that perfectly separates the positive examples from the negative ones. If your data isn't arranged that way, if the boundary between the classes is curved or complex, or involves interactions between the inputs, a single perceptron simply cannot learn it. It doesn't have the mathematical capacity. The most famous illustration of this is the XOR problem. XOR, exclusive or, takes two binary inputs and outputs 1 if the inputs are different and 0 if they're the same. 0, 0 gives 0, 1, 1 gives 0, but 0, 1 gives 1, and 1, 0 gives 1. If you plot these four cases on a two-dimensional grid, the positive cases and the negative cases are arranged diagonally, and no single straight line can separate them. A perceptron can learn AND, it can learn OR, but it cannot learn XOR. And this tiny example, this almost toy-like logical function, turned out to be a harbinger of a vast class of problems that perceptrons simply couldn't handle. Now, there's a nuance here that is crucial and that often gets lost in the standard telling of this story. Minsky and Papert knew perfectly well that you could overcome these limitations by using multiple layers of perceptrons, stacking them so that the output of one layer feeds into the input of the next, creating what's called a multi-layer network. With enough hidden layers, you can learn arbitrarily complex patterns. XOR? Trivial for a two-layer network. But, and this was the devastating catch, in 1969, nobody had a reliable, practical algorithm for training the hidden layers. You could see the error at the output, but how did you trace it backward through the network to assign blame to individual weights in the layers that weren't directly visible? That was an unsolved problem. Rosenblatt's learning rule only worked for single-layer networks. The hidden layers were a black box, and nobody knew how to teach them. Minsky was, by temperament, not someone who suffered fools or tolerated hype. He was brilliant, sharp-tongued, and often intimidating. He had been critical of the extravagant claims made about perceptrons for years, and while the Perceptrons book did not technically say that multi-layer networks were hopeless, it focused specifically on single-layer limitations. The overall tone was deeply pessimistic about the entire neural network enterprise. The book was widely read as a funeral notice for the field, and the effect was swift and brutal. Funding dried up. Graduate students were advised to work on other topics. Researchers who persisted with neural networks found themselves marginalized, unable to get grants or publish papers. The field entered its winter, a long, cold period of near-total neglect that lasted the better part of 2 decades. Frank Rosenblatt himself died in 1971, on his 43rd birthday, in a sailing accident on Chesapeake Bay. His boat capsized and he drowned. The exact circumstances have never been fully clarified, and with his death, the figurehead of the neural network movement was gone, along with much of the original energy and optimism. But machine learning itself didn't die. Not at all. The neural network approach specifically went into hibernation, yes. But the broader idea that machines could learn from data was very much alive. It simply took different forms. And during the 1970s and 1980s, while neural networks gathered dust, other approaches were thriving, some of them developing into genuinely powerful and practical tools. One of the most important was the decision tree. The idea is wonderfully intuitive. Think of it as a flowchart that a machine builds automatically from data. You're a doctor trying to figure out if a patient has a particular condition. You ask, does the patient have a fever? If yes, ask, how high? If above a certain temperature, ask, have they traveled recently? And so on, branching at each question, narrowing down the possibilities, until you reach a diagnosis or a prediction. A decision tree algorithm does exactly this, but it builds the flowchart itself, from examples. You give it a table of past cases, symptoms, test results, outcomes, and the algorithm figures out the most informative sequence of questions. It finds the features that split the data most cleanly, and it arranges them into a hierarchical tree structure. J. Ross Quinlan, a computer scientist from Australia, developed the most influential family of decision tree algorithms. His ID3 algorithm in the early 1980s and its refined successor, C4.5, published in 1993, became workhorses of applied machine learning. Decision trees had practical virtues that other methods struggled to match. They were fast to train and fast to use. They could handle both numerical data and categorical data, things like yes, no, or red, blue, green. They dealt gracefully with missing values, which is a constant problem in real-world data. And perhaps most importantly, they were interpretable. You could look at the tree the algorithm produced and trace the decision logic from top to bottom. You could explain, in plain language, exactly why the model was making the prediction it was making. In fields like medicine, banking, and law, where decisions must be explainable and auditable, this transparency was enormously valuable. A doctor who uses a decision tree to help diagnose patients can point to the exact path of reasoning. A loan officer can explain why an application was denied. You can't do that as easily with many other machine learning methods. And even today, that remains one of the great tensions in the field, the trade-off between accuracy and interpretability. Meanwhile, the statistics community, which had always been adjacent to but somewhat separate from the computer science community, was developing its own rich tradition of learning from data. Statisticians had been refining Bayesian methods, regression techniques, and probability theory for decades, and by the 1970s and 1980s, they had an impressive toolkit. There was logistic regression, which could predict not just yes or no, but the probability of an outcome. How likely is it that this patient has diabetes, given their blood sugar level and BMI? There were Bayesian networks, which could model complex webs of interrelated variables, capturing the probabilistic relationships between dozens of factors simultaneously. And there was K-nearest neighbors, a method so simple it barely seems like it should work. To classify a new data point, you just look at the K most similar points in your training data and go with the majority. If your 5 nearest neighbors include 3 cats and 2 dogs, you call it a cat. That's the entire algorithm. No model. No training step. You just memorize all your data and compare new cases to old ones. It sounds almost too naive to work, but for many problems, it works remarkably well. And out of all this work came some of the most important ideas in the entire field. Deep, subtle insights about what it really means for a machine to learn well. Not just to memorize, but to generalize. So let me slow down here, because this is genuinely one of the foundational concepts of machine learning, and understanding it, even at an intuitive level, gives you a kind of skeleton key to the whole field. It's called the bias-variance trade-off, and once you see it, you can't unsee it. Imagine you're trying to predict house prices based on the size of the house. You have a data set, houses that recently sold, with their square footage and their sale price. And you want to fit a model through those data points that will let you predict the price of a new house based on its size. You have choices about how complex to make your model. The simplest option is a straight line. You draw a line through the scatter of data points, and it captures the general trend. Bigger houses cost more. The line probably doesn't pass through many of the points exactly. Most points will be a little above or a little below. But the general direction is right. That's a high bias model. It makes a strong assumption. The relationship is linear, and because of that assumption, it will systematically miss certain real patterns. Maybe housing prices actually curve upward steeply for very large houses, or maybe there's a plateau in the mid-range. The straight line will miss those subtleties. That systematic error, that tendency to be wrong in a predictable way because your model is too simple, that's the bias. Now go to the other extreme. Instead of a straight line, draw a wildly wiggly curve that passes through every single data point exactly. Zero error on your training data. Perfect fit. But think about what you've actually done. You've memorized every quirk, every random fluctuation, every bit of noise in the data. One house sold for less because the sellers were divorcing and wanted out fast. Another sold for more because 3 bidders got into a war over it. A third sold below market because the listing photos were terrible and nobody came to the open house. Those are random factors, noise that has nothing to do with the fundamental relationship between size and price. Your wiggly curve has faithfully captured all of it, treating every random blip as a meaningful pattern. And when you try to use that curve to predict a new house, one that wasn't in your training data, it will give you wild, unreliable predictions, because the noise from the old data has nothing to do with the new house. That erratic sensitivity to the specific training data, that's the variance. The art and science of machine learning is, in a very real sense, about navigating between these two dangers, finding a model that's complex enough to capture the real patterns, but simple enough to ignore the noise. Not too rigid, not too flexible. And this trade-off is universal. It shows up in every machine learning method, in every problem domain, in every application. It's one of those deep, recurring themes that once you understand, you see everywhere. And researchers developed practical tools for managing it. Cross-validation, holding out some of your data, training on the rest, and testing on what you held back to honestly measure how well your model generalizes. Regularization, adding a mathematical penalty that discourages the model from becoming too complex, from putting too much weight on any one feature, or fitting the data too closely. These techniques gave practitioners principled ways to avoid the twin traps of underfitting and overfitting. Simple ideas, in retrospect, but they made an enormous practical difference. Now, while neural networks were frozen in their winter, the rest of artificial intelligence didn't stop. Far from it. The 1970s and 1980s were actually a boom time for a very different approach to making machines intelligent, an approach that was, in many ways, the exact opposite of what Rosenblatt and the neural network researchers had been trying to do. Instead of building machines that learned from data, this approach built machines that were programmed with knowledge. Expert systems, they were called, and for about 15 years, they were the dominant paradigm in AI. Here's the idea behind an expert system. You find a human expert, a doctor who's very good at diagnosing blood infections, say, or a geologist who's very good at identifying promising sites for mineral exploration. And you sit down with that expert for weeks or months, and you extract their knowledge. You ask them, when you see this symptom, what do you consider? If the patient has these lab results, what diagnoses do you rule out? What rules of thumb do you use? What are the red flags? And you encode all of this into a computer program as a set of if-then rules. If the patient has a fever and the white blood cell count is elevated and the culture shows gram-positive bacteria, then consider staphylococcal infection with probability 0.7. Hundreds or thousands of rules like this, carefully crafted and curated, forming a knowledge base that the machine could reason over. One of the most famous early expert systems was Mycin, developed at Stanford in the mid-1970s by Edward Shortliff. Mycin was designed to help doctors diagnose bacterial infections and recommend antibiotics. And it actually worked reasonably well. In testing, it performed about as well as, or in some cases better than, many human doctors on the specific task of diagnosing blood infections. Another landmark system was Dendrol, which could analyze mass spectrometry data to identify chemical compounds. R1, later called XCON, was developed at Carnegie Mellon for Digital Equipment Corporation and could configure VAX computer systems, a task that had previously required specialized human engineers and was costing DEC millions of dollars in mistakes. By the early 1980s, expert systems were big business. Companies were spending millions of dollars building them. Japan launched its ambitious fifth-generation computer project in 1982, which aimed to build a new generation of intelligent machines based largely on knowledge representation and logical reasoning. The AI industry was booming, but expert systems had a fatal flaw, and it was the same flaw that Turing had presciently identified back in 1947 when he compared the rule programming approach to handing a child an encyclopedia. The problem was called the knowledge bottleneck. Building an expert system required a person called a knowledge engineer to sit with human experts and manually extract, formalize, and encode their knowledge as explicit rules. This process was extraordinarily tedious, expensive, and fragile. Human experts often couldn't articulate their own expertise. They relied on intuition, on pattern recognition, on a kind of tacit knowledge that resisted being broken down into neat if-then rules. A doctor might know, from years of experience, that a patient looked sick in a way that was hard to pin down. The color of their skin, the way they held themselves, a subtle quality in their voice. How do you encode that into a rule? You can't, really. And even when experts could articulate their rules, the rules were often incomplete, inconsistent, or situation-dependent in ways that made them difficult to maintain. As expert systems grew larger, they became increasingly brittle. They worked well within the narrow domains they'd been designed for, but the moment you stepped outside that domain, even slightly, they failed, sometimes catastrophically and without warning. They couldn't generalize. They couldn't handle situations that their rules didn't cover, and they couldn't learn from their mistakes. Every new situation, every new edge case, required a knowledge engineer to go back to the expert, extract a new rule, and manually add it to the system. The systems grew more complex, more fragile, and more expensive to maintain. By the late 1980s, the expert system boom was fading. Japan's fifth-generation project, after consuming enormous resources, failed to achieve its ambitious goals. Companies that had invested heavily in expert systems started writing off those investments. And the AI field entered another period of disillusionment. The second AI winter, sometimes called the AI winter of the late 1980s and early 1990s. And here's what's really interesting about this. From the perspective of our story, the failure of expert systems was, in hindsight, a powerful argument for exactly the approach that the neural network researchers had been advocating all along. The knowledge bottleneck demonstrated that you couldn't build intelligent systems by manually programming in all the rules. There were too many rules. They were too hard to extract. They were too brittle, too specific, too inflexible. What you needed was a way for the machine to acquire knowledge from experience, to look at thousands of examples and figure out the patterns itself, to learn, which was, of course, precisely what machine learning was designed to do. But the machine learning that flourished during the expert system era and beyond wasn't the neural network variety. It was the statistical variety. The decision trees, the Bayesian methods, the nearest neighbor algorithms we've already talked about. And there's a whole additional story here about the cultural divide between the AI community and the statistics community, a divide that shaped the development of machine learning in ways that are still felt today. For decades, statisticians and AI researchers had been working on remarkably similar problems: how to make predictions from data, how to classify objects, how to find patterns. But they used different languages, published in different journals, went to different conferences, and often had very little idea what the other community was doing. Statisticians thought of themselves as rigorous scientists, grounded in probability theory and mathematical proof. Many of them looked at AI researchers as undisciplined dreamers, building elaborate systems based on heuristics and hand-waving. AI researchers, for their part, often found statisticians overly conservative, obsessed with theoretical guarantees that had little practical relevance, and blind to the bigger picture of building intelligent machines. This divide meant that important ideas often took years to cross the boundary. Techniques that were well known in statistics took a long time to reach the machine learning community, and vice versa. Leo Breiman, the statistician at Berkeley who invented random forests, actually gave a famous lecture in 2001 called Statistical Modeling: The Two Cultures, in which he argued that the statistics community was too fixated on elegant probabilistic models and was ignoring the messy, powerful, prediction-focused approaches, like neural networks and decision trees, that the machine learning community was developing. It was a provocative argument, and it started a conversation that, in many ways, is still ongoing. But by the early 2000s, the two communities were beginning to converge. Machine learning researchers were adopting the rigorous mathematical tools of statistics, hypothesis testing, confidence intervals, formal error analysis. Statisticians were becoming interested in the large-scale computational methods and the flexible, non-parametric models that the machine learning community was pioneering, and both communities were being drawn together by the gravitational pull of the same force: data. Data in quantities that neither community had ever dealt with before. Data that demanded new methods, new tools, new ways of thinking. And somewhere in the midst of this convergence, as the expert systems were failing, and the statisticians were arguing, and the neural network faithful were keeping their quiet vigil, the practical toolkit of machine learning was growing into something remarkably capable. You could build systems that detected credit card fraud by learning patterns of legitimate and suspicious transactions. You could build spam filters that improved every day. You could build recommendation engines that learned your preferences from your behavior. You could build speech recognition systems that, while not yet good enough for casual conversation, could handle structured commands and simple dictation. None of this was flashy. None of it made newspaper headlines, but it was real, it was useful, and it was getting better. Machine learning was quietly embedding itself into the infrastructure of daily life, working behind the scenes in ways most people never noticed, and it was learning, getting better, adjusting its weights, refining its predictions, one example at a time. That quiet, practical success was laying the groundwork for what came next. Because when the neural networks finally came back, when the computing power and the data and the algorithms finally converged in the way that Hinton and LeCun and Bengio had been waiting for, hoping for, working toward for 30 years, they didn't arrive in a vacuum. They arrived in a world that already had a rich, diverse, battle-tested machine learning ecosystem, decision trees, and random forests for tabular data, SVMs for classification, Bayesian methods for probabilistic reasoning, ensemble techniques for robust prediction, cross-validation for honest evaluation, regularization for preventing overfitting. All of those ideas, all of those tools, had been refined and proven during the long years when neural networks were absent. And when deep learning arrived and changed everything, it didn't replace all of those other tools. It added to them. It conquered specific domains, vision, language, audio, where its ability to learn hierarchical representations from raw data gave it an insurmountable advantage. But for many other problems, especially problems with structured tabular data, the older methods remained competitive, sometimes superior. The machine learning landscape didn't narrow. It expanded, and the diversity of tools available to a practitioner in 2015 or 2020 was far greater than at any previous point in the field's history. And then, in the mid-1980s, the neural networks came back from the dead. After nearly 2 decades in the wilderness, 2 decades of minimal funding, of graduate students being warned away, of researchers quietly switching to other topics just to keep their careers alive, the idea of learning with multi-layer neural networks came roaring back to life. And the breakthrough that made it possible had a name: backpropagation. Now, the history of backpropagation is itself a fascinating case study in how ideas get discovered, forgotten, rediscovered, and then finally recognized. The core mathematical concept, a method for efficiently computing derivatives through a chain of composed functions, sometimes called automatic differentiation in reverse mode, was described by a Finnish mathematician named Seppo Linnainmaa in his master's thesis in 1970. Linnainmaa wasn't thinking about neural networks at all. He was working on a general problem in numerical analysis, but the mathematical technique he described was exactly the tool that neural network researchers needed. Then, in 1974, an American researcher named Paul Werbos went further. In his PhD thesis at Harvard, Werbos explicitly proposed using this backward-flowing derivative calculation to train multi-layer neural networks. He spelled it out. This is how you solve the credit assignment problem. This is how you figure out which weights in the hidden layers are responsible for the error at the output. He wrote it all down, and almost nobody noticed. His thesis was filed away in the Harvard Library and gathered dust. The AI community wasn't reading PhD theses about neural network training methods in 1974. They had moved on. The winter was too cold. What finally changed everything was a paper published in 1986 in the journal Nature, one of the most prestigious scientific journals in the world, by David Rumelhart, Geoffrey Hinton, and Ronald Williams. This paper described backpropagation clearly, demonstrated it working on several compelling problems, and appeared at precisely the moment when the intellectual climate was ready for it. The community had grown dissatisfied with the limitations of the rule-based expert systems that had dominated AI through the 1970s and early 1980s. People were hungry for a new approach, and here it was. So let me try to explain what backpropagation actually does, because the core idea is genuinely intuitive once you get past the notation. And it's worth understanding, because this one technique, this one algorithm for adjusting numbers inside a mathematical structure based on errors, is the engine that drives essentially all of modern deep learning. Every voice assistant, every image classifier, every language model, all of them learn through some variant of backpropagation. Remember the fundamental problem. You have a neural network with multiple layers. Data flows in at the input, gets transformed by each layer in turn, and produces a prediction at the output. You compare the prediction to the correct answer and compute the error, the gap between what the network said and what it should have said. Now you want to adjust the weights, the connection strengths, inside the network to make the error smaller. For the weights in the last layer, this is straightforward. You can see directly how they contributed to the error and nudge them accordingly. But what about the weights in the layers before that? The hidden layers? The ones that aren't directly connected to the output? Their contribution to the error is indirect, mediated by all the layers between them and the output. How do you trace the blame backward through the chain? Here's an analogy that might help. Imagine a long game of telephone, where a message passes through 10 people. The final person announces the message, and it's garbled, wrong. You can immediately correct person number 10 because you can hear what they said and compare it to what they received. But what about person number 5? Their mistake propagated forward through 5 more people, getting mixed up with their mistakes along the way. To figure out how much person 5 contributed to the final garble, you'd need to trace backward through the chain, accounting at each step for how much each person distorted the signal. That's essentially what backpropagation does. It uses the chain rule of calculus, a mathematical tool for computing derivatives of composed functions, to propagate the error signal backward through the network, layer by layer, computing at each weight exactly how much that weight contributed to the final error. And then it nudges each weight by a tiny amount in the direction that would reduce the error. This process, compute the error, propagate it backward, adjust all the weights by a small amount, then repeat with the next training example, is called gradient descent. And the metaphor most people use to describe it is that of a blindfolded hiker trying to find the lowest point in a hilly landscape. You can't see the terrain, but you can feel the slope beneath your feet. So at each step, you move in whichever direction feels steepest downward. Step by step, you descend into the valley. You might not find the absolute lowest point. You might get stuck in a local dip, a small valley that isn't the deepest one in the whole landscape. But in practice, especially with large networks and lots of data, gradient descent tends to find solutions that work remarkably well. The publication of the 1986 paper was a watershed. Neural networks were back in the conversation. Researchers started training multi-layer networks on a variety of problems, and the results were encouraging. Handwritten digit recognition. The U.S. Postal Service actually deployed a neural network to read zip codes on envelopes. Speech recognition, medical diagnosis, financial prediction. Networks with 2 or 3 hidden layers could learn patterns that no single-layer perceptron could touch. And Geoffrey Hinton, one of the 3 authors of that paper, became the central figure in the revival. Hinton's story is extraordinary. He was born in London in 1947 into a family of remarkable intellectual distinction. His great-great-grandfather was George Boole, the mathematician whose Boolean algebra, the logic of zeros and ones, and or and not, is the foundation of every digital circuit ever built. Hinton studied experimental psychology at Cambridge, and then pivoted to artificial intelligence. And in the early 1970s, just as the rest of the field was abandoning neural networks, he became convinced that the brain-inspired approach was fundamentally right, that the way to build intelligent machines was not to program them with rules, but to let them learn from data through networks of simple processing units that adjust their connections through experience. He was almost alone in this belief, and the price of that conviction was high. Through the 1970s and early 1980s, Hinton struggled to get funding for his neural network research. He moved from Britain to the United States and then to Canada, partly because the intellectual climate was more tolerant there. Canadian funding agencies were willing to support unconventional research that American agencies wouldn't touch. He spent years working on ideas that most of his peers considered a dead end. Imagine choosing to spend the prime years of your career on a topic that the leaders of your field had publicly declared hopeless. That takes either deep insight or deep stubbornness, and in Hinton's case, it was both. The backpropagation paper was his first great vindication. But the full vindication, the one that would transform the entire technology industry, was still decades away, and the road between would be long and frustrating. Because here's the thing about the late 1980s and the 1990s. Backpropagation worked, but it worked inconsistently. Training neural networks was more art than science. You had to choose the right number of layers, the right number of neurons in each layer, the right learning rate, how big a step to take with each gradient descent update. And if you got any of these wrong, the network might fail to learn at all, or learn too slowly, or learn the training data perfectly, but fail on new data. The error surfaces were treacherous, full of local minima, plateaus, and narrow ravines that made gradient descent unreliable. And networks with many layers, truly deep networks, the kind that would eventually prove most powerful, were especially problematic. The gradient signal tended to either vanish as it was propagated backward through many layers, becoming so tiny that the early layers barely learned at all, or explode, becoming so large that the weights flew off to infinity. This was called the vanishing gradient problem, and it was a genuine showstopper for deep architectures. For many practical applications during this period, the older, simpler techniques, decision trees, logistic regression, k-nearest neighbors, performed just as well as neural networks and were far easier to use. You didn't need to fiddle with architectures and learning rates. You didn't need to wait hours or days for training to converge, and you could actually understand what the model was doing. Neural networks were interesting, yes, promising in some sense, but they were not yet dominant, not even close. And this brings us to another towering figure in the history of machine learning, someone whose contribution is sometimes overshadowed by the neural network narrative, but is truly foundational. Vladimir Vapnik. Born in Uzbekistan in 1936, Vapnik grew up in the Soviet Union and began his scientific career at the Institute of Control Sciences in Moscow. Starting in the early 1960s, he and his colleague Alexei Chervonenkis began developing a mathematical theory of learning that was rigorous in a way that nothing else in the field was. They asked the deepest possible questions. When does a learning algorithm actually work? Under what conditions can you trust that a model trained on a finite sample of data will perform well on new data it's never seen? Are there fundamental mathematical limits on what can be learned? The framework they built, statistical learning theory, or VC theory, was elegant, abstract, and profoundly important. It introduced concepts like the VC dimension, a measure of a model's capacity to fit complex patterns, and proved mathematical bounds on generalization error, the gap between how well a model performs on its training data and how well it performs on truly new data. For the first time, there was a rigorous theory telling you why some learning algorithms generalize and others memorize, why simpler models sometimes beat complex ones, and how the amount of training data interacts with model complexity to determine performance. But for decades, this theoretical work was largely unknown outside the Soviet Union. The Cold War made academic exchange difficult. Soviet journals weren't widely read in the West. Vapnik published important results, but they didn't reach the people who could use them. It wasn't until Vapnik emigrated to the United States in 1990 and joined Bell Labs in New Jersey that his work began to reach a wider audience. And it was at Bell Labs that he used his decades of theoretical insight to build something practically revolutionary. He called it the support vector machine, the SVM, and the elegance of the idea still takes my breath away a little. Imagine two groups of data points, let's say healthy patients and sick patients, plotted in some abstract space based on their lab results. You want a boundary between them that will let you classify new patients correctly. Many boundaries might work, infinitely many, in fact. But Vapnik asked, which boundary is best? And his answer was brilliant in its simplicity. The best boundary is the one with the widest margin, the biggest gap between the boundary and the nearest data points on either side. Think of it like building a wall between two communities, and you want the wall to be as far from both communities as possible, so that a person who's near the wall but on one side is still clearly, comfortably on that side. The wider the gap, the more robust the classification. The data points that sit right on the edge of the margin, the closest points to the boundary, are the support vectors. They're the critical cases, the hardest examples, the ones that determine where the boundary goes. Move a point that's far from the boundary, and nothing changes. Only the support vectors matter. And then came the kernel trick. The idea that made SVMs work on problems where no simple boundary could separate the classes. Without going deep into the mathematics, the kernel trick lets you implicitly project your data into an enormously high-dimensional space where a linear separation becomes possible, even though the original data was hopelessly tangled in its original space. And the genius is that you never actually compute coordinates in this high-dimensional space. You use a mathematical function, the kernel, that tells you distances and relationships in the high-dimensional space without ever explicitly visiting it. It's like being able to measure distances on a mountain range using only a topographic map. You get the right answers without actually climbing the mountains. SVMs dominated machine learning through the 1990s and early 2000s. They won competitions. They set benchmarks. They were the gold standard for text classification, image categorization, bioinformatics, handwriting recognition, and they had a theoretical pedigree, Vapnik's own learning theory, that gave practitioners confidence that they were doing something mathematically sound, not just hacking. But the SVM's reign coincided with the rise of another family of techniques, ensemble methods, that took a completely different philosophical approach. The ensemble idea starts with a question that sounds almost paradoxical. Can you get something great by combining a bunch of things that are merely okay? The answer, it turns out, is emphatically yes. And the person who demonstrated this most convincingly was Leo Breiman, a statistician at Berkeley, with a unique combination of theoretical depth and practical, real-world experience. Breiman had spent years consulting for businesses and government agencies, working with messy data and imperfect models, before returning to academia. He knew, from hard experience, that the perfect model was a fantasy. Every model was wrong in some way. The question was whether you could exploit the fact that different models were wrong in different ways. In the mid-1990s, Breiman introduced bagging, bootstrap aggregating. The recipe is simple. Take your training data. Create many slightly different copies of it by randomly sampling with replacement. Some data points appear multiple times, others get left out entirely. Train a separate model on each copy. Now, when you need a prediction, have all the models vote. Majority wins. Why does this work? Because each model, trained on slightly different data, makes slightly different errors. And if those errors are sufficiently diverse, if the models aren't all wrong in the same way at the same time, then the errors cancel out in the aggregate, like measurement errors averaging out when you take many readings of the same quantity. The ensemble is more stable and more accurate than any individual member. In 2001, Breiman combined bagging specifically with decision trees to create random forests, adding an extra layer of randomization. Each tree is only allowed to consider a random subset of features at each split point, which further diversifies the ensemble. And random forests became an instant classic. They were fast. They were robust. They handled missing data and mixed variable types gracefully. They were hard to overfit, and they performed well on a staggering variety of problems, from ecology to genomics to customer analytics. Even today, in many practical applications, a well-tuned random forest is extremely difficult to beat. Meanwhile, Yoav Freund and Robert Shapir developed boosting, a different philosophy of ensemble learning, where bagging builds models independently and averages them. Boosting builds models sequentially, with each new model focusing specifically on the examples that the previous models struggled with. The first model does its best. It gets some right and some wrong. The second model upweights the examples the first one missed, concentrating its effort on the hardest cases. The third model focuses on what the first two still can't handle, and so on. The final ensemble is a weighted combination of all the models, with each model's weight reflecting its overall accuracy. Freund and Shapir proved, with beautiful mathematics, that this sequential refinement could turn any collection of weak learners, models barely better than random guessing, into a strong learner with arbitrarily high accuracy. Their AdaBoost algorithm won the Gödel Prize. And later variants, gradient boosting machines, and especially XGBoost, developed by Tianqi Chen in 2014, became the dominant technique in applied machine learning for nearly a decade. In Kaggle competitions, where thousands of data scientists compete on prediction problems, XGBoost was so dominant that it became a running joke. Whatever the problem, whatever the domain, someone would win with XGBoost. So by the early 2000s, the machine learning landscape was rich and competitive. SVMs with their mathematical elegance, random forests with their brute force reliability, boosting methods with their sequential refinement. Neural networks, still alive but still somewhat marginal, hampered by training difficulties and widespread skepticism. Bayesian methods, logistic regression, nearest neighbors, decision trees, a whole diverse ecosystem of techniques, each with its partisans and its sweet spots. And behind all of them, a tidal wave was building. The world was drowning in data, and nobody had yet figured out how to drink from the fire hose. The internet was growing exponentially. Google, founded in 1998, was indexing billions of web pages and processing hundreds of millions of search queries every day. Each query was data. Each click was data. Amazon was tracking the purchases, browsing habits, and reviews of millions of customers. Netflix was collecting movie ratings, hundreds of millions of them. Facebook launched in 2004 and began accumulating the social graphs, photos, status updates, and likes of hundreds of millions of users. YouTube appeared in 2005, and within a year, people were uploading tens of thousands of videos per day. Twitter followed in 2006. Smartphones proliferated after the iPhone launched in 2007, and suddenly billions of people were carrying around devices that generated continuous streams of location data, accelerometer data, photos, messages, and app interactions. Every digital interaction, every click, every swipe, every purchase was being recorded somewhere. The total amount of data being generated each day was measured in exabytes, billions of gigabytes. And for machine learning researchers, this was like the discovery of a new continent, because machine learning algorithms are data hungry. They're almost always limited by the quality and quantity of their training data. A model that's mediocre with 1,000 examples might be excellent with 100,000 and spectacular with 10 million. And for the first time in history, 10 million examples, or 100 million, or 1 billion were becoming available. This era gave us one of the most compelling public experiments in machine learning's history, the Netflix Prize. In October 2006, Netflix offered $1 million, real money, a headline-grabbing amount, to anyone who could improve the accuracy of its movie recommendation system, called Cinematch, by 10%. They released a huge data set, about 100 million movie ratings from around 480,000 users on roughly 17,000 movies, and opened the competition to the world. Build a better recommender. Show us a 10% improvement on a specific statistical metric, and we'll write you a check for $1 million. The response was staggering. Over 40,000 teams from more than 180 countries registered. Academics, hobbyists, professional data scientists, high school students, retirees. Everyone piled in, and the competition became a crucible for machine learning techniques. Teams tried absolutely everything. Matrix factorization, which decomposes the giant user movie rating matrix into latent factors. Neighborhood methods, which find similar users or similar movies. SVMs and boosted decision trees. Restricted Boltzmann machines, a type of neural network, and dozens of hybrid approaches that no one had thought of before. For 3 years, teams pushed, incremented, combined, and struggled toward the 10% threshold, and several important lessons crystallized. First, data mattered more than algorithms, up to a point. Teams that found clever ways to extract more signal from the data consistently outperformed teams that used fancier mathematical machinery. Second, no single model could reach the goal. The teams that came closest invariably blended many different approaches. The final winner, Bellcore's Pragmatic Chaos, an alliance of teams that had merged to combine their diverse methods, used an ensemble of over 100 individual algorithms, each one contributing something slightly different. The whole was far greater than any of its parts. And third, there was a gap between mathematical accuracy and genuine usefulness. Netflix found that even the winning solution, which was measurably better by the contest's metric, didn't transform the user experience in the way you might expect from a 10% improvement. People are complicated. What makes a recommendation feel right isn't always the same thing that minimizes prediction error. That gap between optimizing a number and delighting a human remains one of the central challenges of applied machine learning. But all of this, the SVMs, the random forests, the Netflix prize, the explosion of data, was the prologue. The main event was about to begin, and it was driven by the convergence of three things that were, individually, each unremarkable, but together would prove to be the most consequential combination in the recent history of technology. The first was data. We've covered that. An unprecedented ocean of labeled examples, images, text, audio, transactions, interactions. The second was hardware, specifically the GPU, the graphics processing unit. This is one of those beautiful accidents of technological history. GPUs were designed to render video game graphics, their entire purpose, when NVIDIA and ATI were developing them in the 1990s and 2000s, was to draw polygons on a screen at 60 frames per second, to shade surfaces, calculate lighting, project textures, render millions of pixels, fast, in parallel. And to do all of that, GPUs evolved a particular architecture, thousands of small, simple computational cores, all working simultaneously. A CPU has a few very powerful cores that handle one task at a time, very quickly. A GPU has thousands of weaker cores that each handle a simple task, but all at once. It's the difference between one chef who can cook anything and 1,000 cooks who each know how to stir a pot. And it turns out that the mathematics of training neural networks, multiply matrices, add vectors, apply simple functions element by element, repeat, maps almost perfectly onto the architecture of a GPU. Neural network training is inherently parallel. You can process thousands of neurons simultaneously, because the computations within a layer are independent of each other. You can process large batches of training examples at once. The shape of the computation fits the shape of the hardware, like a key fitting a lock. Researchers began experimenting with GPU-accelerated neural network training around 2009 and 2010, and the speedups were dramatic. Not 10% faster, not twice as fast, but 10, 50, 100 times faster than CPU-only training. A model that would have taken months to train on CPUs could be trained in days on GPUs. And suddenly, the deep architectures that Hinton and others had been dreaming about, networks with many layers, millions of parameters, trained on millions of examples, became practical. The third ingredient was the people. A small, almost impossibly stubborn band of researchers who had never abandoned neural networks, even when the rest of the field told them, year after year, that they were wrong. Geoffrey Hinton, at the University of Toronto, still pushing the approach he'd championed for 3 decades. He had trained a generation of graduate students who shared his conviction, and many of them would go on to reshape the field. Yann LeCun at New York University had been working on convolutional neural networks, a specific architecture designed for processing images, since the late 1980s. LeCun had shown, back in the 1990s, that convolutional nets could read handwritten digits well enough to be deployed commercially. AT&T and several banks used his system, called LeNet, to process millions of handwritten checks. But the broader computer vision community remained unconvinced. They stuck with hand-engineered features and SVMs. Yoshua Bengio, at the University of Montreal, was exploring deep architectures, sequence models, and the theoretical challenges of training deep networks. Together, Hinton, LeCun, and Bengio, later dubbed the godfathers of deep learning, kept the flame alive through the long years when it seemed like it might go out entirely. And then came 2012. The year everything changed. The stage was ImageNet, and the story of ImageNet begins with Fei-Fei Li. Li came to the United States from China as a teenager, studied physics at Princeton, and went on to become a computer vision researcher at Stanford. And in the mid-2000s, she had an insight that was both simple and deeply contrarian. The bottleneck in computer vision, she believed, wasn't algorithms, it was data. The field was spending enormous energy on designing clever mathematical features and sophisticated classifiers, but training and testing them on small, curated datasets, a few thousand images, maybe tens of thousands. Li believed that if you gave learning algorithms truly massive amounts of visual data, millions of images spanning thousands of categories, they would learn to see in ways that no hand-engineered system could match. So she set out to build that dataset. It was years of painstaking, unglamorous work. She and her students organized a taxonomy of visual categories: dog, cat, car, bridge, banana, church, running shoe, grand piano, everything you can think of. And then they recruited workers through Amazon Mechanical Turk, tens of thousands of people, paid a few cents per image, to label millions of photographs scraped from the internet. Is this a golden retriever or a Labrador? Is this image clear enough to use? Does this photo actually show a saxophone, or is the saxophone just barely visible in the background? The quality control alone was a massive logistical challenge. By the time it was done, ImageNet contained over 14 million labeled images in more than 20,000 categories. It was, by far, the largest and most diverse visual dataset ever created. Starting in 2010, the ImageNet Large-Scale Visual Recognition Challenge invited research teams to build systems that could classify images from a subset of ImageNet, about 1.2 million training images in 1,000 categories. Each year, the best systems would compete, and the error rates would inch down. In 2010, the winning error rate was about 28%. In 2011, it dropped to about 25%. Progress was steady but incremental, driven mostly by improvements in handcrafted feature engineering, methods with names like SIFT, HOG, and Fisher vectors, combined with classifiers like SVMs. The improvements felt hard-won and modest. And then, in 2012, a team from the University of Toronto entered a system called AlexNet. It was built by Alex Krzyzewski, a graduate student, with supervision from Geoffrey Hinton. Ilya Sutskever, another of Hinton's students, contributed to the theoretical foundations. AlexNet was a deep convolutional neural network, 8 layers, with about 60 million parameters, trained on 2 NVIDIA GTX 580 GPUs, consumer-grade gaming cards, over the course of 5 or 6 days. And it achieved an error rate of about 15.3%. The second-place team was at 26.2%. Let that sink in for a second. The gap between first and second place was nearly 11 percentage points. In previous years, the gap had been 1 or 2 points at most. This wasn't an improvement. This was a rupture. It was as if, in an Olympic swimming event where the world record had been dropping by tenths of a second each year, someone suddenly swam the race 3 seconds faster. The rest of the community was stunned. How? What did they do differently? The answer was deep learning. A deep neural network, trained end-to-end on raw pixels, had learned its own features. its own hierarchy of representations, and those learned features were dramatically better than anything humans had hand-designed over decades of careful engineering. The early layers of AlexNet had learned to detect edges, just like the hand-engineered Gabor filters that computer vision researchers had been using for years. But the deeper layers had learned to combine those edges into textures, shapes, parts, and objects in ways that were more nuanced, more flexible, and more powerful than anything a human could have designed. The network had, in a sense, done the feature engineering itself, and it had done it better than the experts. The fallout was immediate and total. Within 2 years, every competitive entry in ImageNet was using deep neural networks. The hand-engineered feature approach was abandoned, virtually overnight, after decades of dominance. And the revolution spread far beyond image recognition. Deep learning was applied to speech recognition, and accuracy improved dramatically, good enough that voice assistants became practical for everyday use. Machine translation was overhauled, with neural approaches replacing the statistical phrase-based systems that had dominated for years. Drug discovery, protein structure prediction, medical imaging, autonomous driving, robotics, one domain after another was transformed by the realization that deep neural networks, given enough data and enough compute, could learn to do things that no hand-designed system could match. Now, let me add something important here about how convolutional neural networks actually process images, because this is one of the cleverest engineering ideas in all of machine learning, and understanding it helps explain why deep learning works so much better than anything that came before on visual tasks. A standard neural network connects every neuron in one layer to every neuron in the next. That's fine for small inputs, but for an image, even a modest 224 by 224 pixel image in 3 color channels, you'd have over 150,000 input values. Connecting every one to every neuron in the next layer would create an absurd number of connections and parameters. The network would be enormous, slow to train, and almost certainly would overfit. Yann LeCun's brilliant insight, developed in the late 1980s drawing partly on earlier work by Kunihiko Fukushima in Japan, was to exploit the structure of images. In images, patterns are local. An edge, a corner, a texture appears in a specific region, and the same pattern can appear anywhere in the image. An edge is an edge, whether it's in the top left corner or the bottom right. So instead of connecting everything to everything, a convolutional network uses small filters, tiny grids of weights, maybe 3 by 3 or 5 by 5 pixels, that slide across the entire image, computing a response at each position. Each filter detects one particular pattern: a vertical edge, a horizontal gradient, a small blob of color. And because the same filter is applied everywhere, the network automatically learns to recognize a feature, regardless of where it appears in the image. This is called translation invariance, and it's enormously powerful. You stack many of these convolutional layers, and between them, you insert pooling layers that gradually reduce the spatial resolution, shrinking the representation while preserving the important patterns. The result is a hierarchy. Early filters detect simple features. Later filters combine those into complex patterns. And the final layers of the network make the actual classification decision. And the whole thing, every filter, every weight, is learned through backpropagation. The network discovers what patterns to look for, all by itself. LeCun demonstrated this with LeNet in the early 1990s, a network that could read handwritten digits with remarkable accuracy. It was deployed commercially by AT&T and major banks for processing handwritten checks, reading millions of them every day. But the broader computer vision community remained skeptical. LeCun's approach worked on the relatively constrained problem of digit recognition, but people doubted it could scale to the messy, varied, infinitely complex visual world of natural images. It took ImageNet and AlexNet 20 years later to prove them wrong. And there's another piece of the deep learning story that deserves attention: the development of techniques that finally solved the vanishing gradient problem and made truly deep networks practical. Remember, in the 1990s, networks with more than a few layers were almost impossible to train because the gradient signal weakened as it was propagated backward. Several innovations, developed over the course of the 2000s and early 2010s, chipped away at this problem. Better activation functions, the rectified linear unit, or ReLU, introduced around 2010, replaced the older sigmoid function and largely eliminated the vanishing gradient issue for feed-forward networks. Batch normalization, proposed by Sergei Ioffe and Christian Szegedy in 2015, stabilized training by normalizing the inputs to each layer. Residual connections, introduced by Kai-Ming He and colleagues at Microsoft Research in 2015, allowed networks to skip connections between layers. If a layer's contribution wasn't needed, the signal could bypass it entirely. This seemingly simple trick allowed researchers to train networks with over 100 layers, dramatically deeper than anything that had been possible before. These weren't glamorous breakthroughs. They didn't make headlines, but they were essential engineering advances that made the deep learning revolution practically possible. Without ReLU, without batch normalization, without residual connections, AlexNet might have been an isolated success rather than the beginning of a revolution. Science progresses through leaps of imagination, but also through patient, unglamorous engineering. The kind of work that makes the difference between a technique that works in a lab demo and one that works at scale in the real world. And it's worth pausing here to appreciate something about the trajectory of this field that is genuinely unusual in the history of technology. The ideas behind deep learning, neural networks, backpropagation, convolutional architectures, were all developed decades before they became practical. The core techniques were available in the 1980s and 1990s. What was missing was scale, enough data to train on, enough compute to process it. The ideas were right, but the infrastructure hadn't caught up. And then, when the infrastructure did catch up, when GPUs became powerful enough, when data became abundant enough, when software frameworks like TensorFlow and PyTorch made implementation practical, the impact was not gradual, it was sudden and overwhelming. Like a dam breaking, or a seed that has been waiting underground for decades and then shoots up in a single season when the conditions are finally right. The lesson, if there is one, is that in technology, timing is almost everything. An idea can be correct and still fail if the world isn't ready for it. And it can go from failure to triumph in the span of a few years when the missing ingredients finally arrive. This pattern, a long period of latent potential, followed by explosive realization, is what makes the history of machine learning so dramatic. Bayes in the 1740s, ignored for decades. Gauss and Legendre in the early 1800s, doing machine learning without machines. Rosenblatt in the 1950s, building a learning machine that was 20 years ahead of its time. Werbos in 1974, writing a thesis about backpropagation that nobody read. Hinton in the 1970s and 1980s, keeping faith in neural networks through the long winter. And then AlexNet in 2012, and then the Transformer in 2017, and then ChatGPT in 2022. And suddenly, the world is different. The gap between the dream and its realization was, in some cases, more than 200 years. That's patience on a civilizational scale. And then, In a moment that felt almost like science fiction, deep learning conquered a challenge that many experts had predicted was decades away. In March 2016, AlphaGo, a system built by DeepMind, a London-based AI lab that Google had acquired in 2014, played a 5-game match against Lee Sedol, one of the greatest Go players of all time. Go is an ancient board game, over 2,500 years old, with a simplicity of rules that belies an almost incomprehensible depth of strategy. The number of possible board positions is estimated to be around 10 to the power of 170, a number so large it dwarfs the number of atoms in the observable universe. Brute force search, the approach that had conquered chess, was completely hopeless for Go, and because Go's strategy relies so heavily on pattern recognition, intuition, and long-term planning, qualities that seemed distinctly human, many AI researchers believed that computers were still 10 or 20 years away from competing with the best human players. AlphaGo won 4 games to 1. It wasn't close, and during Game 2, AlphaGo played Move 37, a stone placed in a position that no human Go player had ever considered, a move that violated centuries of Go intuition, a move so strange that the live commentators fell silent in confusion. Lee Sedol left the room for 15 minutes. When the dust settled and the game was analyzed, Move 37 turned out to be brilliant. It reshaped the entire board in a way that gave AlphaGo a subtle but decisive advantage. The AI had found something that thousands of years of human play had missed. That moment, that single move, became an icon of what deep learning could do. AlphaGo also brought a different branch of machine learning into the spotlight: reinforcement learning. Unlike the supervised learning we've been discussing, where you learn from labeled examples, from pairs of inputs and correct outputs, reinforcement learning works through trial and error, guided only by a reward signal. An agent takes actions in an environment, observes the consequences, and receives a reward, positive or negative, that tells it how well it did. Over thousands or millions of trials, the agent learns a strategy, a policy, that maximizes its cumulative reward. It's the kind of learning that a child does when playing a new game, or that an animal does when exploring its territory. You try something, you see what happens, you adjust. The idea dates back to the 1950s, but it was the combination of reinforcement learning with deep neural networks, deep reinforcement learning, that produced AlphaGo's superhuman play. The network learned not from being shown expert moves, but by playing millions of games against itself, discovering strategies that no human teacher could have provided. And what made the moment culturally significant went beyond the technical achievement. Go occupies a special place in East Asian culture. In Korea, in China, in Japan, it's not merely a game, but an art form, a practice of discipline and intuition and beauty. Lee Sedol was not just a player, but a national icon. His defeat by a machine touched something deeper than a scientific result. It raised questions that people had been asking in the abstract, but now felt concretely. What does it mean when a machine can outthink a human at a task that requires creativity and intuition? What is left that is uniquely, irreducibly human? Those questions don't have easy answers. But the fact that a learning algorithm forced us to ask them, that itself tells you something about where this story has arrived. But the deepest and most far-reaching revolution in deep learning was still ahead, and it started with a paper published in 2017 by 8 researchers at Google. The paper was called "Attention is All You Need," and the architecture it introduced, the transformer, would become the foundation for the most powerful AI systems ever built. Before the transformer, The standard approach to processing text with neural networks was the recurrent neural network, or RNN. Recurrent networks process sequences one element at a time, maintaining an internal state that gets updated at each step. Read word 1, update state. Read word 2, update state, and so on. It works, and for years it powered machine translation, speech recognition, and text generation. But it has two serious problems. First, it's inherently sequential. You can't process word 5 until you've finished with words 1 through 4, which means you can't parallelize the computation, which means training on large datasets is painfully slow. And second, recurrent networks struggle with long-range dependencies. By the time the network reads the 100th word of a paragraph, the information from the first word has been passed through so many updates that it's been diluted, distorted, often lost entirely. It's like the game of telephone. The message degrades with each relay. The transformer solved both problems with a single mechanism, self-attention. And here's the idea, as simply as I can explain it on a quiet night. Instead of reading a sentence one word at a time, left to right, the transformer looks at all the words at once, and for each word in the sentence it asks, which other words in this sentence are most relevant to understanding this word right now? It computes a relevance score, an attention weight, between every pair of words. The word it in a long sentence can look all the way back to the subject of the sentence and figure out what it refers to. The word bank can check whether river or account is nearby and adjust its representation accordingly. Each word builds a richer version of itself, a contextualized representation, by attending to the words around it. And because the attention calculations are done for all words simultaneously, in parallel, you can process an entire sentence, or even a long document, in one pass, throwing massive GPU power at it. That parallelism was the key to scaling. Recurrent networks were bottlenecked by their sequential nature. Transformers were free. The impact was immediate and sweeping. In 2018, Google released BERT, bidirectional encoder representations from transformers. BERT was trained on a massive corpus, the entirety of English Wikipedia plus a large collection of books, using a training task called masked language modeling. You take a sentence, randomly hide some of the words, and ask the model to predict the hidden words based on the surrounding context. It's like a fill-in-the-blank exercise, billions of times over. And from this simple exercise, BERT developed representations of language that were remarkably powerful. It broke records on question answering, sentiment analysis, text classification, and a dozen other benchmarks, often by large margins. Google integrated it into its search engine, and search results got measurably better. OpenAI, meanwhile, was pursuing a slightly different approach with GPT, Generative Pre-trained Transformer, where BERT reads text in both directions to predict missing words. GPT reads left to right and predicts the next word. Just the next word. What comes after this? It's the simplest possible language task. You train the model on enormous quantities of text, books, websites, articles, code, conversations, and at each position, it tries to predict the next token. That's the entire training objective. But something profound happens when you scale this up. When the model has billions of parameters and has been trained on hundreds of billions of words, the mere act of predicting the next word forces it to develop an incredibly rich understanding of language and, apparently, of the world that language describes. To predict the next word in a passage about orbital mechanics, you need to know some orbital mechanics. To predict the next word in a legal argument, you need to understand legal reasoning. To predict the next word in a joke, you need to understand humor and timing and surprise. The knowledge isn't programmed in. It's a byproduct of the prediction task. It emerges from scale. GPT-2, released in February 2019, could generate coherent, stylistically appropriate paragraphs of text that often read as if a human had written them. OpenAI initially withheld the full model, worried about its potential for generating disinformation. GPT-3, released in June 2020, was a massive leap. 175 billion parameters, trained on a corpus of hundreds of billions of words. And it demonstrated something nobody had fully anticipated: few-shot learning. You could give GPT-3 a handful of examples of a task. Here are 3 English sentences and their French translations. Now translate this one, and it would continue the pattern correctly, without any additional training, without updating any weights, just from the context of the prompt. It was, in effect, learning new tasks at the moment of use. And then, in November 2022, OpenAI released ChatGPT, GPT fine-tuned with reinforcement learning from human feedback, a technique where human evaluators rate the model's responses, and the model is trained to produce outputs that humans judge as helpful, accurate, and safe. ChatGPT hit the public like an earthquake. 1 million users in 5 days. 100 million within 2 months. The fastest adoption of any technology product in history. People used it to write emails, debug code, plan trips, explain complex topics to their children, draft business proposals, compose poems, brainstorm names for their dogs. It wasn't perfect. It confidently stated things that were completely wrong, a phenomenon called hallucination. It could be manipulated into saying things its designers hadn't intended, but the sheer breadth, fluency, and apparent understanding it displayed were unlike anything the public had ever interacted with. Machine learning, which had been quietly developing in labs and academic conferences for 70 years, was suddenly the most discussed technology in the world. Generative AI, the branch of machine learning focused on creating new content rather than just classifying or predicting, also deserves a moment of attention as we wind down this story. Ian Goodfellow, while a graduate student at the University of Montreal in 2014, invented generative adversarial networks, or GANs, after what's probably the most productive argument in the history of a bar. He was debating with friends about generative models, went home, coded up his idea that night, and it worked on the first try. The idea was elegantly adversarial. Pit 2 neural networks against each other. One, the generator, tries to create fake images. The other, the discriminator, tries to tell the fakes from real images. Through this competitive dance, the generator gets better and better at producing convincing images, because any imperfection that the discriminator catches becomes a signal for improvement. GANs produced some of the first truly photorealistic AI-generated faces and sparked an explosion of creative applications and, inevitably, concerns about deepfakes. Later, a different approach, diffusion models, emerged as the foundation for image generation systems like DALL-E, Midjourney, and Stable Diffusion, which can create detailed, sometimes stunning images from text descriptions. The basic idea behind diffusion models is beautifully counterintuitive. You take real images and gradually add noise to them, step by step, until they become pure static. Then you train a neural network to reverse the process, to remove noise, step by step, recovering the original image from the static. Once trained, you can start from pure random noise and have the network denoise it into a coherent image, guided by a text prompt that tells it what to create. It's like learning to sculpt by first learning to erode, understanding destruction so well that you can run it backward into creation. And this is where I want to pause and let the story breathe for a moment. Because underneath all the hype and the headlines, underneath the breathless coverage and the genuine concerns about safety and jobs and truth, there is something profoundly, almost movingly simple at the heart of all of this. A large language model is a mathematical function. It takes a sequence of word fragments as input and outputs a probability distribution over what fragment might come next. Every word it generates is a prediction, a bet, based on patterns extracted from its training data. And all of its apparent knowledge, all of its seeming understanding, is encoded in numbers, hundreds of billions of weights, arranged in the layers of a transformer architecture. And those weights were set by backpropagation, by gradient descent, by the same fundamental technique that Rumelhart, Hinton, and Williams described in a Nature paper in 1986, the same technique that Paul Werbos proposed in his forgotten 1974 thesis. The same underlying principle, adjust the parameters to reduce the error, that traces all the way back to Arthur Samuel's checkers program in the 1950s, to Frank Rosenblatt's perceptron, to Gauss and Legendre, finding the curve that best fit their noisy astronomical measurements in the early 1800s, to Thomas Bayes, in a quiet rectory in Tunbridge Wells, working out how to update beliefs based on evidence. Adjust, learn, try again. That's the thread that runs through this entire story, from the 18th century to today. It's the same idea, applied at wildly different scales, in wildly different contexts, but always the same essential process. See the error, adjust the model, try again. And here's what I find most beautiful about this, lying here thinking about it on a quiet night. The core ideas of machine learning are not arcane or inaccessible. They are, at bottom, descriptions of something deeply familiar, learning from examples, finding patterns, adjusting when you're wrong, trying again. These are things that every child does every single day without anyone teaching them how. A toddler learns to recognize her mother's face, not by studying anatomy, but by seeing that face thousands of times. In morning light and evening shadow, smiling and serious, close up and across the room, and gradually building an internal representation of what that face is. A child learns language not by memorizing grammar rules, but by absorbing millions of words in context, hearing them used in real situations, and slowly, unconsciously, extracting the patterns, subject before verb, adjective before noun, the rising intonation of a question, the rhythm of a sentence that feels right, even though no one can quite explain why. The remarkable insight of machine learning is that this ancient process, learning from experience, can be captured in mathematics, implemented in circuits, and scaled to levels that no biological brain could match. The algorithms we've talked about tonight didn't come from nothing. They came from watching how learning already works in nature, and trying to bottle it, to formalize it, to make it reproducible and scalable. And the fact that it works, that a mathematical process, inspired by how neurons fire, can learn to see, to read, to speak, to translate, to reason, that fact is, however you look at it, extraordinary. But this story has never been primarily about mathematics or about machines. It's been about people, about Alan Turing, brilliant and tragic, imagining learning machines in an era when most people didn't know what a computer was, about Arthur Samuel, patient and practical, watching his checkers program teach itself in a quiet lab at IBM, about Frank Rosenblatt, bold and optimistic, building his perceptron and imagining a future that was 20 years ahead of its time, about Minsky and Papert, intellectually fearless, publishing the critique that sent neural networks into a winter from which many thought they would never emerge, about Geoffrey Hinton, stubbornly faithful through decades of isolation, refusing to abandon an idea that the entire field had dismissed, and being vindicated so completely that his work now touches the life of nearly every person on Earth. About Fei-Fei Li, patiently assembling ImageNet when no one understood why it mattered, creating the catalyst for a revolution. About Alex Krzyzewski, a graduate student with 2 gaming GPUs, training the network that drew a line between before and after. About the 8 authors of Attention is All You Need, who set out to improve machine translation and accidentally built the architecture for the most transformative technology of the 21st century. These are human stories, stories of conviction and doubt, of ideas born too early and vindication arriving late, of careers spent in the wilderness, of moments when someone looked at a result and realized that everything had changed. The machines themselves don't have these stories. They don't feel the quiet thrill of a late-night breakthrough, or the sinking weight of a rejected paper, or the 10-year ache of believing in something that no one else believes in, but the people who built them do. And the history of machine learning is, in the end, their history. The story of a curious, restless species that has always been fascinated by the question of what it means to learn, and that built, over the course of 2 centuries, something that might eventually help answer that question. Where this goes next, no one can say for certain. The pace of progress is faster than it has ever been. Models grow larger and more capable by the month. New architectures and training paradigms emerge constantly. Multimodal systems that process text, images, video, and audio together are becoming routine. And the questions about safety, about truth, about power, about what it means to be human in a world where machines can do more and more of what humans used to do exclusively, those questions are becoming more urgent with every new capability. But those are questions for the morning, when the light comes back and the world demands answers. Right now, the ideas are settling into place, layer by layer, the way they always have, slowly at first, a formula scratched out in a clergyman's study, a method of fitting curves to noisy data by candlelight, and then faster, building on themselves, until the whole thing begins to move, with a momentum that feels almost like it has a life of its own. And maybe the most remarkable thing about this story, the thing that gives it a kind of poetic symmetry, is that the field of machine learning has itself learned in exactly the way it describes. It learned from its mistakes, from its winters and its dead ends, and its promises that came too early. It adjusted its weights. It tried again. It found new paths when the old ones were blocked, and slowly, unevenly, through decades of setback and breakthrough, it arrived somewhere extraordinary. That's learning. That's the whole point. The process and the product are the same thing. Sleep well tonight. The machines will keep running in the dark, adjusting their parameters, processing another batch of data, getting imperceptibly better at whatever it is they've been asked to do. And somewhere, in a data center you'll never see, a model is reading another sentence, generating another prediction, learning one more small thing. The learning isn't finished. It may never be, and that might be the most human thing about it. Good night.